Good morning, students. Welcome back to Mathematics Science Discussion via Facebook Live. Before we start our lesson, make sure that you are physically and mentally prepared for our today's topic. You must have your pen and your notebook with you so that you can take down some important notes during discussion. If you are ready, then let us begin. Our today's lesson is about right triangle similarity theorem and special right triangle theorem. At the end of the discussion, you must be able to prove the conditions of right triangle similarity theorem and special right triangle theorem. Since we are talking about proving, let us have a short activity entitled Look Back as a recap of the said topic. In this, you are going to identify if the two given triangles are similar or not. Type similar if the two triangles are similar, and type not similar if the two triangles are not similar. Type your response on the comment section below. You are given 10 seconds to identify and to type your answer. Are you ready? Let's begin. Number 1. Refer to the given figures. Timer starts now. Time is up. The answer is similar. Notice that the three corresponding sides are proportional. Hence, they are similar by SSS similarity theorem. Number 2, refer to the given figures. Timer starts now. Time is up. The answer is similar. The two corresponding sides are proportional, and the corresponding included angle is congruent. Hence, they are similar by SAS similarity theorem. Next, number 3, refer to the given figures. 10 seconds. Timer starts now. Time is up. The answer is not similar. The given three corresponding sides are not proportional, and there is no given measure of angle. Hence, the two triangles are not similar. Number 4, refer to the given figures. Timer starts now. Time is up. The answer is not similar. The given two corresponding sides are proportional, but their included angle is not congruent. Hence, the two triangles are not similar. Number 5, refer to the given figures. Timer starts now. Time is up. The answer is similar. If you are going to complete the labels for the measure of unknown angles, the two triangles are both 40 degrees, 50 degrees, 90 degrees triangle. Three corresponding angles are congruent. Hence, the two triangles are similar by AAA similarity postulate. Thank you for your very active participation in our review activity. I hope you were able to recall the previously discussed postulate and theorems of triangle similarity. Let us have a brief recall of the statement of the triangle similarity postulate and theorems. What are the postulate and theorems of triangle similarity? AAA similarity postulate is the first, where two triangles are similar if and only if all their corresponding angles are congruent. Second, AA similarity theorem. Two triangles are similar if two corresponding angles are congruent. Number three, the SAS similarity theorem. Two triangles are similar if two pairs of corresponding sides are proportional and included angles are congruent. Number four, SSS similarity theorem. Two triangles are similar if their three corresponding sides are proportional. Next is, let us identify the parts of a triangle as a last part of our recall. Given is a right triangle RON. The angle O measures 90 degrees, which makes the triangle a right triangle. The opposite side of the right angle is the longest side, and it is called the hypotenuse. The other two sides are called leg. Now that the parts of a right triangle are identified, let us now discuss the theorems for the similarity of right triangle. For the first theorem, right triangle similarity theorem, as shown in the figure, triangle ACB is a right triangle with right angle at angle C. CD is the altitude of the given right triangle. With this, the theorem states that in any right triangle, the altitude to the hypotenuse divides the triangle into two right triangles, which are similar to each other and to the given right triangle. To show the proof, given CD is the altitude to the hypotenuse, AB, of the right triangle ABC. Prove that triangle ADC is similar to triangle ACB, triangle CDB is similar to triangle ACB, and triangle ADC is similar to triangle CDB. Kindly refer to the figure for further understanding of the given. To easily visualize the similarity, draw the two right triangles formed by the altitude CD. And they are triangle ADC and triangle CDB. In naming the triangles in similarity, use a correct order, like in this given. The original triangle is named starting from its shortest leg going to the longer leg. This order must also be applied in naming the two triangles formed by the altitude CD. Starting from the shortest leg, AD, going to the longer leg, DC, hence the triangle is named triangle ADC. For the next triangle, starting from the shortest leg, CD, going to the longer leg, DB, hence the triangle is named triangle CDB. To prove this theorem, we will use the two columns proof. Since there is no given measure of sides, we will not use SSS similarity theorem or SAS similarity theorem to prove similarity of two triangles. Instead, we will use the angles to prove the triangle similarity by either AAA or AA similarity theorem. Write the given first. Triangle ABC is a right triangle with right angle C and the altitude CD. The reason is given. Since CD is altitude, then it is perpendicular to AB. We can state that angle ADC and angle CDB are right angles. The reason? Definition of an altitude of a triangle. Triangle ADC and triangle CDB contains right angle. Therefore, we can state that triangle ADC and triangle CDB are right angles. Why? It is because of the definition of right triangle. Angle ADC is congruent to angle ACB. Angle CDB is congruent to angle ACB. And angle ADC is congruent to angle CDB because each pair of angles is both right angles. The reason is any two right angles are congruent. One corresponding angle is congruent to triangles ACB and ADC, which is the angle ACB and angle ADC. Let us find another congruent corresponding angle. Notice in the triangle ACB and triangle ADC, they both contain angle A. Hence, angle A is congruent to angle A by reflexive property. Two angles of triangle ACB is congruent to corresponding two angles of triangle ADC. Hence, triangle ADC is similar to triangle ACB by AA similarity theorem. The first pair of triangles was proved similar. Next is to prove that triangle CDB is similar to triangle ACB. This pair of triangles has one congruent corresponding angle, which is angle CDB and angle ACB. Let us find one more congruent corresponding angle. The two triangles both contains angle B. Hence, angle B is congruent to angle B by what reason? It is reflexive property. Two angles of triangle ACB is congruent to corresponding two angles of triangle CDB. Hence, triangle CDB is similar to triangle ACB by AA similarity theorem. And the second pair of triangles was proved similar. And lastly, using statement 6 and statement number 8, we can state that triangle ADC is similar to triangle CDB. What do you think is the reason? If you answered transitive property, you are right. The third pair of triangles was proved similar. It is now proved that given a right triangle with altitude C to the hypotenuse, two right triangles were formed by the altitude. The given right triangle is similar to each of the right triangles formed by the altitude to the hypotenuse. And the two right triangles formed are similar to each other. And to apply this theorem, let us answer this example. In right triangle GEO, EM is an altitude. Name three similar triangles. Name at least one angle congruent to each angle, angle EMO, angle G, and angle GEM. Referring to the figure, separate the two triangles formed by the altitude. By right triangle similarity theorem, the three triangles are similar to each other. Hence, triangle GEO is similar to triangle EMO, triangle GEO is similar to triangle GME, And triangle EMO is similar to triangle GME. And for the second question, angle EMO is a right angle. Hence, it must be congruent to right angle also. With this, angle EMO is congruent to angle GME. Angle EMO is congruent to angle GEO. For angle G is congruent to angle MEO. And for angle GEM is congruent to angle EOM. For the theorem, following the right triangle similarity theorem is the what we call geometric mean theorem. As shown in this figure, the theorem states that in a right triangle and altitude to the hypotenuse is given, the altitude is the geometric mean of the segments into which it separates the hypotenuse. And letter B, each leg is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. What does geometric mean stand for? The geometric mean is a special type of getting the average. It is done by multiplying all the numbers in a given set of data and then taking its positive nth root. To see its illustration, given triangle ACB and CD is an altitude. Separating the three triangles, we have triangle BCA, triangle BDC, and triangle CDA. For triangle BDC and triangle CDA, the proportion BD is to CD as CD is to AD is formed by getting the relationship of longer leg to shorter leg of each triangle. By cross multiplication property or the means extremes law of proportion, CD square is equal to AD times BD. Get the positive square root of each side. CD is equal to the square root of AD times BD. So, the altitude is the geometric mean of the two segments of hypotenuse. Next, for right triangle BCA and triangle CDA. The proportion AB is to AC as AC is to AD is formed by getting the relationship of hypotenuse to shortest leg of each triangle. By cross multiplication or the means extremes law of proportion, AC square is equal to AD times AB. Get the positive square root of each side. AC is equal to the square root of AD times AB. So leg AC is the geometric mean of the length of its adjacent segment of hypotenuse and the total length of the hypotenuse. Next is for triangle BCA and triangle BDC, the proportion BC is to AB as BD is to BC is formed by getting the relationship of longer leg to hypotenuse of each triangle. By cross multiplication property or the means extremes law of proportion, BC square is equal to BD times AB. Get the positive square root of each side. BC is equal to the square root of BD times AB. So, leg BC is the geometric mean of the length of the adjacent segment of hypotenuse and the total length of the hypotenuse. And let us apply now this theorem in these examples. For example 1, given triangle MAT is a right triangle and AH is an altitude. If AH is equal to 12, MH is equal to 9, find HT, TM, and AM. Solving for HT, let HT be equal to X. To solve this, we will use geometric mean theorem, which involves the altitude and the hypotenuse, since these quantities have given length. AH is equal to the square root of MH times HT. Since we are solving for the length of HT, and it is inside the radical, we're going to square both sides of the equation. We get AH squared is equal to MH times HT. The length of AH is 12, the length of MH is 9, and for HT is X. Square of 12 is 144, and 9 times X is 9X. Divide both sides of the equation by 9, we get 16 is equal to X. And by symmetric property, X is equal to 16. Since HT is equal to X, hence HT is equal to 16. Solving for TM, we simply add the length of MH and HT. MH is equal to 9 and HT is equal to 16. Hence, the length of TM now is equal to 25. Solving, lastly, for AM, use the geometric mean theorem that involves the leg and hypotenuse. AM is equal to the square root of MH times TM. Substituting the values of MH and TM, AM squared is equal to the square root of 9 times 25. 9 times 25 is equal to 225, and getting its square root, that is equal to 15. Thus, AM is equal to 15. You can find the length of AT using geometric mean theorem also, or you can use the Pythagorean theorem. Find the length of AT after this today's session and show your answer to our discussion teacher tomorrow for checking. For the second example, given triangle MAR is a right triangle and AK is perpendicular to MR. Find X plus Y plus Z. From the given figure, the length of MK is 4 and the length of KR is 9. Solving for X, since X is the altitude, we will use the geometric mean that involves the altitude, and that is X is equal to the square root of MK times KR. Substitute the values of MK and KR. MK is 4 and KR is 9. 4 times 9 is 36, and the square root of 36 is equal to 6. Hence, X is equal to 6. Solving for the second variable, Y. Since Y is one of the legs of the right triangle, we will use the geometric mean that involves the leg, and that is Y is equal to the square root of MK times MR. Substitute the values of MK and MR, and 4 times 13 is equal to 52. Get its square root, we have 2 square root of 13. Hence, Y is equal to 2 square root of 13. And lastly, solving for the variable Z. Since Z is one of the legs of the right triangle, we will use the geometric mean that involves the leg, and that is Z is equal to the square root of KR times MR. Substitute the values of KR and MR, and 9 times 13 is equal to 117. And the square root of 117 is equal to 3 square root of 13, and that is the value of the variable z. Now that we have the values of x, y, and z, we can solve for their sum. And that is 6 plus 5 square root of 13. For the next theorem is the median theorem. The theorem states that the median to the hypotenuse of a right triangle is 1/2 as long as the hypotenuse. This means that in right triangle MAT, AH is the median to the hypotenuse. Thus, AH is equal to 1/2 of MT. To further understand this, let us answer this example. Determine the value of x. From the given figure, the length of the hypotenuse CI is equal to 24. HP is represented by x, and it is a median to the hypotenuse, since its intersection to the hypotenuse passes through the midpoint as shown by the tick mark. Applying the median theorem to solve for the value of x, x is equal to 1/2 of CI. The length of CI is equal to 24, and 1/2 of 24 is equal to 12. Hence, the value of the variable x is 12. Another example, determine the value of x and y. From the figure, the length of RO is equal to 15, and the length of ON is 8. The length of the hypotenuse RN is represented by the variable x, and the length of the median OL is equal to y plus 12. Solving now first for x, use Pythagorean theorem to right triangle RON, and that is x squared is equal to 8 squared plus 15 squared. The square of 8 is equal to 64, and the square of 15 is equal to 225. Get its sum, we get 289, and then get the positive square root of both sides of the equation, we get x is equal to 17. So we now have the value of the variable x. So let's proceed now to solving for y. Since y is contained in the median, therefore, we will use the median theorem. The median OL is 1/2 or equal to y plus 2. Thus, the equation is y plus 2 is equal to 1/2 the hypotenuse x. The obtained value of x is 17. Therefore, substitute 17 to x. And then 1/2 of 17 is 8.5. And then further simplifying, the value of y is equal to 6.5. And that is our answer. We are now done with the theorems of right triangle similarity. Let us now proceed to last part of today's lesson, which is the special right triangle theorem. So we have two theorems for this. First is the 30, 60, 90 triangle theorem. In the figure, given right triangle ACB with right angle at angle C, angle A is 30 degrees and angle B is 60 degrees. The theorem states that in a 30, 60, 90 triangle, the side opposite the right angle is twice, as long as the side opposite the 60 degrees angle is square root of 3 times, as long as the side opposite the 30 degrees angle. From the given figure, AB is the hypotenuse and it is twice as long as the side CB. And the side AC is square root of 3 times as long as the side CB. Let us prove this theorem. Given angle CAB is equal to 30 degrees, angle ABC is equal to 60 degrees, and angle ACB is equal to 90 degrees. Prove that AB is equal to 2BC. Before we proceed to the two columns proof, we will do some construction. From point C, construct segment CD such that BC is congruent to CD. Connect the points A and D. It is now clear that angle ACD is a right angle. Since they are linear pair, so their sum is 180 degrees. And one of the angles is a 90 degrees angle. Thus, it follows that the other angle is also 90 degrees. Since BC is congruent to CD, therefore, we can state that BC is 1/2 of DB, or DB is equal to 2BC. We have a larger triangle here, the triangle ADB. Triangle ADB contains two triangles, triangle ACB and triangle ACD. Now, we are done with doing the construction. Let us proceed to the two columns proof. For the first statement, angle CAB is equal to 30 degrees. Angle ABC is equal to 60 degrees, and angle ACB is equal to 90 degrees. The reason is given. BC is congruent to CD. The reason is by construction. Angle ACB is congruent to angle ACD. Why? They are both right angles, and any two right angles are congruent. AC is congruent to AC. The reason is reflexive property. Triangle ACB is congruent to triangle ACD by what? That is by SAS postulate, since two corresponding sides and included angle are congruent to both triangles. Angle ADC is congruent to angle ABC, and since angle ABC measures 60 degrees, then angle ADC measures 60 degrees also. Why? Later, that will be given. Let me finish with angle CAD is congruent to angle CAB. And since angle CAB measures 30 degrees, then angle CAD measures 30 degrees also. So what do you think will be the reason here? If you answered CPCTC, then you are correct. Angle CAD plus angle CAB is equal to angle A. The reason is, yes, that is angle addition postulate. 30 degrees plus 30 degrees is equal to angle A. How did this happen? This is by the law of substitution. If we're going to get the sum of the two angles 30 plus 30, that is equal to 60 degrees is equal to angle A. And that is by the addition property of equality. Each of the angles of triangle ADB measures 60 degrees. Hence, triangle ADB is an equilateral triangle. The reason is definition, obviously, of equilateral triangle. Since triangle ADB is an equilateral triangle, therefore, all its sides are congruent. Hence, we can state that AB is equal to DB. The reason is definition of equilateral triangle. DB is equal to 2BC. Where did it come from? That is by construction that we made a while ago. And for the final statement, AB is equal to 2BC, the reason for this is transitive property using the statement 12 and 13. And it is now proved that the hypotenuse is twice the length opposite the 30 degrees angle. Let us now prove that the length of side opposite the 60 degrees angle is square of 3 times the length of side opposite the 30 degrees angle, or square root rather. For the opposite side of 60 degrees angle, use Pythagorean theorem, where the angle opposite 30 degrees is x and the hypotenuse is 2x. We have AC squared is equal to x squared, or AC squared plus x squared is equal to the square of 2x. The square of 2x is equal to 4x squared. And then for this, by addition property of equality, we have AC squared is equal to 4x squared minus x squared. And simplifying this, AC squared is equal to 3x squared. Get the positive square root of both sides of the equation. We have AC is equal to square root of 3x. The proof is complete now for the length of sides of 30 degrees, 60 degrees, 90 degrees, special right triangle. We can say that the sides are in the ratio 1 is to square root of 3 is to 2. Let us now answer this example. Find the length of the missing sides of the given triangle RON with angle R measures 60 degrees, angle O measures 90 degrees, and angle N measures 30 degrees. The sides are represented by A, B, and C. The length of side B is equal to 6. B is the shortest leg, and C is the hypotenuse. Solving for C, since C is the hypotenuse, therefore its length is twice the shortest leg B. Thus, the equation is C is equal to 2B. Substitute the value of B, which is 6, and multiply this, that is equal to 12. Hence, C is equal to 12. And solving for A is the longer leg. Thus, it is square root of 3 times the shortest leg. The equation now is A is equal to the square root of 3B. Substitute the value of B, which is 6, and multiply it, we get 6 square root of 3, and that is the answer to this example. Let us now proceed to the second theorem of the special right triangle, and that is the 45 degrees, 90 degrees triangle theorem. In the figure, given triangle PHI with a right angle at angle H and angle P and angle I both measures 45 degrees. The theorem states that in a 45-45-90 triangle, both legs are congruent and the length of the hypotenuse is square root of 2 times as long as either of the two legs. It can also be called as isosceles triangle theorem. For the proof of this theorem, given triangle ABC is an isosceles triangle with HP is equal to HI is equal to X, PI is equal to C, and measure of angle H is equal to 90. Prove that C is equal to square root of 2x. For the first statement, triangle ABC is an isosceles triangle with HP is equal to HI is equal to X, PI is equal to C, and the measure of angle H is equal to 90. The reason is given. Next, C squared is equal to X squared plus X squared. This is formed by using the Pythagorean theorem. C squared is equal to 2x squared. That is by addition property of equality or APE. And then C is equal to the square root of 2x by extracting the square of both sides. It is now proved that the length of the hypotenuse is square root of 2 times as long as either of the two legs. We can state that the ratio of the sides is 1:1 is to square root of 2. Let us answer this example. Find the length of the diagonal represented by the variable x. From the given figure, the length of each side is equal. Thus, the figure is a square. The diagonal EA is represented by the variable x. Each diagonals of a square bisects a pair of opposite angles, which is in reference to our previous lesson in quadrilaterals. Thus, diagonal EA bisects angle E and angle A. Since each angle of a square measures 90 degrees, angle E is bisected with a measure of 45 degrees each part. And angle A is bisected with a measure of 45 degrees each part also. Thus, triangle TEA is a 45, 45, 90 triangle. Solving for x, apply the theorem for 45, 45, 90. That is x is equal to the square root of 2 multiplied by the length of the leg. Substitute the length of the leg, which is 5, and multiply it. X is equal to 5 square root of 2. And this is the answer. And we are done. I hope you learned a lot from our today's discussion. If there are part of the lesson that confused you, feel free to ask it to your online discussion teacher tomorrow. For the generalization, let us sum up everything we discussed today. Right triangle similarity theorem states that in any right triangle, the altitude to the hypotenuse divides the triangle into two right triangles which are similar to each other and to the given right triangle. Geometric mean theorem states that given a right triangle and altitude to the hypotenuse, the altitude is the geometric mean of the segments into which it separates the hypotenuse. Letter B, each leg is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. And next, for the median theorem, it states that the median to the hypotenuse of a right triangle is 1/2 as long as the hypotenuse. For the special right triangle theorem, the 30-60-90 triangle theorem states that in a 30-60-90 triangle, the side opposite the right angle is twice as long as the side opposite the 30 degrees angle. And the side opposite the 60 degrees angle is square root of 3 times as long as the side opposite the 30 degrees angle, and it gives the ratio of the sides 1:3, or square root of 3:2. And for the 45-45-90 triangle, both legs are congruent, and the length of the hypotenuse is square root of 2 times as long as either of the legs. It can also be called as the isosceles triangle theorem. Okay, no question. Okay, since there is no question given to me by our moderator, we will now proceed to your assignment. You are going to answer this home learning task, and this will be checked together with your teacher during the follow-up discussion tomorrow. Before we end this session, let me leave you this quotation. Knowing what's right doesn't mean much unless you do what's right. Take note this from Franklin Roosevelt. Thank you for attending and actively participating in our today's lesson. I hope that you learned a lot from the discussion. Always stay safe, everyone. Have fun learning. God bless you all.